just want to repeat briefly what we did up to now in these lectures. So first we defined how a neural network looks like. For us, the neural network is just a very complicated function with many, many parameters that I will be able to adapt. And the purpose is to adapt these parameters so that I approximate as well as possible a given function that maps the input to the output. And the way to achieve this is you define some kind of cost function that measures the deviation between the desired outputs and the true output of the network. And then you try to minimize this cost function by adapting all the weights, by tuning all the weights. And the way to do this is simply gradient descent. So you try to change the parameters of the network in just the right way so as to minimize the cost function. And that is known as stochastic gradient descent, simply because in principle the cost function depends on all possible training examples that you could ever think of. But of course in practice you already want to do a training step after seeing only a handful of training examples. And so this is only a stochastic sample of the true cost function. Okay. Then the question that immediately arises is, well, if we want to go this way and we want to do gradient descent, how do we calculate efficiently the derivatives that we need? So the derivatives of the output of the neural network with respect to all its parameters. And remember, a neural network can have thousands of neurons, and it can have even millions of parameters. These are the weights, the connections that connect the neurons. And so to take a gradient with respect to so many variables, that needs to be done efficiently. And it turns out that it's not that hard. The resulting technique is known as backpropagation, but we learned last time that what you apply is basically high school mathematics. So you start by applying the chain rule repeatedly, and then you realize, okay, it contains steps that can be interpreted as a kind of matrix vector multiplication, so that is no longer high school mathematics, but a little bit beyond. And so the way to interpret is that you start from the top of the network and slowly proceed down layer by layer, and in doing so you establish all these gradients. So this is what we discussed last time. And I'd say that at this point we already have gone through both the most important and the most difficult part of these lectures. To remind you of how this works, here again is a graphic that I already displayed last time, trying to illustrate backpropagation. This is our network. Each circle is a neuron. It carries a value at each moment in time. These lowest neurons form the input layer. There you write in the values that correspond to your input sample, for example, the pixel values of an image. And then you go, as you evaluate the network, you would go from one layer to the next layer, calculate linear superpositions and apply nonlinear functions. Do the same again in the next step, going layer by layer to the final output layers. Now, this C here represents the cost function. C depends on the output, and it compares the output of the neural network against the true output that you would want to have. So C is larger when things are not quite good. And so what you want to do is to calculate the derivative of this cost function with respect to all the parameters, which remember are all these connection strengths, all the weights. Now, if, for example, you wanted to calculate the derivative with respect to one of the weights that is related to one of the connections down here between the input layer and the first layer, then the chain of connections that goes from the output layer down to this one is pretty long. And so that is reflected in the fact that if you now want to calculate this gradient, you have to apply many steps of the chain rule to actually go from the output down there to where you actually want to change the weight. And so let's see how this goes in a graphical way. So first you establish what is the derivative of the cost function with respect to the output of the neural network. So that would produce a factor of this sort. This is something we discussed last time. But then you want to learn, okay, if I have this neuron, which really applies a nonlinear function to some kind of linear superposition of its input values, then how do I take the derivative of this? And this is where then the derivative of this nonlinear function f will appear. And then you go on step by step. So if you carry out the chain rule further and take your derivatives, such a connection will contribute as an additional factor the weight of this connection. Then again, you hit a neuron, you have to take the derivative of the nonlinear function, and so on, until finally you reach down to the actual weight with respect to which you wanted to calculate the gradient. Okay, so that's a graphical depiction of what is going on. And if you were to apply this image of executing the gradient, then of course this is only one possible way of connecting the cost function down to one of these neurons, and actually you get many more contributions than that, and you would have to sum over all these contributions, and so it becomes a kind of sum over all possible paths connecting the output to this particular connection that you wanted to change. That is the particular connection with respect to which you wanted to calculate the gradient. Okay. Now this is not the way it's done most efficiently, but the way it's done most efficiently, I already mentioned, is just repeated matrix vector multiplication. And in the end, the overall cost of backpropagation is exactly the same as the overall cost of the forward propagation. So if you can evaluate a network in, I don't know, a millisecond, then also to calculate all the gradients together takes another millisecond. So this is just a summary of what is really done. You start with something that we like to call the deviation vector. At the output layer, it's initialized to something that has to do with the difference between the output of the neural network and the output of the neural network and the desired output. So f of y in is the function that represents the training example, so the desired output. And then you would go down layer by layer, and you would calculate these contributions, but in the end, you only need to do these matrix vector multiplications. Okay. So I skip this. I just want to emphasize once again that all of this, both the forward propagation where you evaluate the network on its input and the backward propagation all together can be written in 30 lines of code. So it's really not that much. And this is very general. So once you have this, you can train arbitrary networks. So to summarize, if we have a neural network, there's a general purpose algorithm, the evaluation of the network, which we call feed forward, and the backpropagation, which is calculating the gradients. But that doesn't mean that you can now attack an arbitrary problem. Rather, there is still some hyperparameters, so-called hyperparameters, that you have to choose. For example, simply the layout of the network. How many layers do you have? How large are these layers? What is the nonlinear function maybe that you choose? These kinds of things. Also, of course, one of the main tasks that you have is to generate the training samples. Either you load them from big databases that already exist or that you have to compile, maybe even by hand. Maybe this is the most critical part of the whole project, where you have to invest the most work. Or alternatively, you can produce these training examples by software. And in physics, this might be simulations. Maybe you have a simulation running on a supercomputer. The input is a few parameters. The output is a full time evolution, a movie even. And then you might have the idea of training a neural network to give you an approximation of this output when it's given these input parameters. Okay. And then finally, you want to train. And even for that, again, there are some choices to be made. You have to choose, for example, a learning rate. So how large is the step when you change the weights, when you change the strengths of the connection during each training step. Or, for example, in each training step, you want to average over a certain number of training samples. That is called a batch of training samples. How large is your batch size? Fine. And so now, let's discuss this particular example in some more detail and have a look at the code. What we can do to illustrate things is to have say, only 2 input values and only 1 output value. And the 2 input values, so why I like this example is because I can interpret these 2 input values as the 2 coordinates in the 2-dimensional plane. So y0 is one of the input neuron values, and y1 is the other value, and I can plot this on the 2-dimensional plane. And then the single output value that I get for each combination of these 2 input values, I can interpret as a function, a scalar function of 2 variables. Or in this case, I can display this function as a color. So for example, if I pick a training example up here, indicated by the circle, so the y0 and y1 coordinates are those of the circle, and then I can read off from this graph what would be the value or the color of this particular point, and that's the output that the neural network should give me for this particular point. If I then choose another point, like the one down here, I get different y0 and y1, and I also get a different output. And I want to be able to train my neural network such that if you give me an arbitrary such picture or an arbitrary function of 2 variables, it should reproduce correctly this function. So this is the neural network you should be thinking of: 2 input neurons, 1 output neuron. And so now I want to quickly switch to the code. Let me go there. All of these code examples you can find out on the website. So on the website machinelearningforphysicists.org, if you scroll down to where you can download the PDF of the lecture notes, you can then also download these examples. There's a link to a folder where you can download these examples. So here what I have on the screen, let me show this to you. So what I have on the screen here are exactly these functions that I was talking about that implement both the feed-forward and the backpropagation. So the first function just applies our nonlinear function f of z. And then this is a function that applies 1 forward step from 1 layer to the next. This is a function that would apply subsequent steps of this to go from the input layer to the output layer. So it goes through all the layers and calculates the output value of the neural network given the input values. And then there's one step of the backpropagation, and here's the full backpropagation. So it takes certain results of the forward pass, which have been stored during the forward pass, and uses them in order to do this backward pass. So this exactly implements the algorithm that we were talking about. And I really invite you to go through this in detail at home, because that's better than just staring at it when you see it here on the screen. And then you can compare against the mathematics, the formulas on the slides, and see that this Python code really implements the backpropagation algorithm. Okay. And so then finally, there's this gradient step, which does nothing else, but it takes the gradients that have been calculated by the backpropagation. So for example here, dw is the derivative of the cost function with respect to the weight in a certain layer, here indicated by the index j. And then it changes the weights of this layer number j in the direction of the negative gradient. And the prefactor is this eta, which we call the learning rate. So that tells me how large are the steps. I will tell you later these steps should not be too large, and they should not be too small either. If they're too small, everything is too slow. If they're too large, you get very large fluctuations. Okay. And then we can now try to train the net to reproduce an arbitrary 2D function. So here I now choose a particular configuration of the network. For example, here 5 layers, and then I indicate what should be the sizes of these layers. So most of the hidden layers simply have 30 neurons. There's nothing particular about this, but this seems to be enough for this purpose here. And another thing is that I initialize my weights and also the biases, which are the other parameters, in a random fashion. So initially the neural network doesn't know anything. It will calculate a random function actually. Okay. And so now I want to define a function and plot it, and that is actually the function that I already showed you on the slides. Basically, it is shown here. So it is shown here. So it's basically a Gaussian together with the absolute value of the sum of the two variables. So this is how it looks like. No special function, but just something that we want to train on. And then I still need to produce my training examples. So what I will do, so here there could be many different choices. For example, I could literally place a grid, a square grid, a fine square grid on this function, and then I could walk through all the points in this grid, and each point represents a training sample, and I could feed that into the network and apply backpropagation and get my gradients and update them. But it's much nicer if you just pick random training samples. This is also with less bias, because otherwise you would start in the upper left corner of the picture, and until you got to the lower right corner of the picture, probably the network has already forgotten what you trained it on when it started. So it's much better to have just random, to pick random positions in this 2D plane. So now I will try to train it. So I took 2,000 batches, and I have to check what was the batch size. Oh, it was 1,000 points. So 2,000 times I fed in parallel 1,000 training samples randomly picked into the network. So in total, I trained it on 2 million, just to make sure that I get a nice result for you. And what you see here is actually the cost function as it evolves during training. So on the horizontal axis, we have these 2,000 batches, each of which again contains already 1,000 points. And here you see the value of the cost function, and you see very nicely that it decreases very rapidly in the beginning and then decreases much more slowly. And that's a typical behavior for a cost function when you train a neural network. In the beginning, it learns some very important rough features of the function that you want to train on, and then it becomes slower, but it still improves. So this is still important. Okay, and now I want to show you, of course, how well the network is doing. So now I want to evaluate it, and I want to evaluate it really on a fine grid. Yeah? I want to evaluate it on a fine grid, and so here I will produce for myself a batch of points that live on a grid, and if you want to know Python trick, this flatten function is the one that I need in order to convert a two-dimensional array into one long one-dimensional array, which is what I need to generate these training examples. Again, it's best if I discuss this in general terms here, and then at home you go through this in some more detail and think about why the individual lines do what they do. Okay. And so then finally, this is the output of the network. So you see, it's not perfect, absolutely not. So this is not exactly the function that I wanted to have. But you see the most important features. Yeah. So the zero line, the line of zeros across the diagonal, and then the maxima are here indicated in the corners. So I scroll up. This would have been the real function that I wanted. This is the neural network approximation that I get. So it's not so bad. And now you could really play around and change the parameters. You could say, for example, oh, let me take less layers, let me take less neurons in the layers, let me train with less training examples, let me train with a larger learning rate, and so on. And so some of these things we will try out in the following. Yes? Okay, so you claim that for such a small... Remember, the cost function is a quadratic function of the deviation, so maybe that misleads you a little bit, because then if the deviation is still 0.1, it would be 0.01. What are the absolute sizes of the function? Yeah, you see the absolute values, even the absolute values themselves for this particular function, just range up to 0.25. So then if you have a deviation of 0.05, it would already be quite visible here. And then you have to square that in order to estimate what that would contribute to the cost function. Also, even if the absolute values are pretty close, then sometimes you could still get features such as these streaks, so to speak, that even if the absolute deviation isn't so large, your eye can easily pick out these features, and then you say, maybe that's not so great. Okay, please. Yes, in principle, the cost function could become 0. That will depend on the exact function you want to train on, of course, and the exact structure of the neural network, and also the nonlinear function that you chose for the neural network. But sure, I mean, I could just initialize one neural network randomly, and then tabulate the results, use them as training examples, or use them as the samples that I care about, and then try to train another neural network that has the exact same structure and the exact same nonlinear function, and it should be able, of course, to reproduce perfectly the first one, because if I choose exactly the same weights, it will precisely reproduce the other neural network. Yeah? So yes, the cost function in principle can become exactly 0, but that's not so much the point here. Yeah? So we want to approximate well complicated functions, and in the end, it's not. I mean, you have to understand this is a toy example, because why would I want to reproduce such a simple scalar function of 2 variables? In the end, I will apply this to functions where the input may be a full image, and the image consists of 10,000 color values. So instead of 2 input neurons, I will have 10,000 input neurons, yeah? And maybe the output is also an image. So then I map 10,000 to 10,000, and then of course I'm living in a much more high dimensional space, yeah? And then I couldn't even hope to go through all the possibilities. I just need to use the training examples that I really care about. So, yeah. Okay. Let's go back here. Okay, so we saw that this works. This is just displaying again how I produce my batch. And now I want to show you another example. What I did was, instead of programming a function that I want to train on, I uploaded a picture, and I converted this picture into, well, function values, so to speak. So the function really uses the picture as a lookup table, and it looks at a certain coordinate and checks what is the color of the picture, and then it will return this color. And now I'm training my neural network on this function, which means essentially I'm training my neural network on this image. So the neural network should try to reproduce this image as well as possible. If you like, it is even an attempt to compress this image, at least if the number of weights in your neural network would be smaller than the number of pixel values that this image has, then it would be a way to compress such an image. Okay, but other than that, the scheme is exactly the same as before. And so now how does this work? Well, you see, this is one of the first, well, after training some episodes, I don't know how many, this is what you get. There are certainly details missing. For example, you don't at all see the outline, the border of this smiley face, but you do already see the most important features, so the 2 eyes and the mouth. And then you go on and on. And so this is now a network with this configuration of layers, so 2 input neurons, of course, 1 output neuron, but then 150, 150, and 100. And it took me, when I did this, 2 minutes of training on my laptop. It took about 4 million samples. So okay, so this is what you get, and this goes on and on. It's just a reminder why these pictures look the way they look like when I use a rectified linear unit for training. So remember the rectified linear unit, if I plug in a number z, it gives me either 0 if the number is negative, or z itself if the number is positive. So if the number has been calculated linearly from 2 coordinates, then what this means, if this is the plane of the 2 coordinates, then, for example, asking where the number is exactly 0 is like asking where a linear superposition of two coordinates is 0. So that's a single equation to set to set such a linear combination to 0 is a single equation. Single equation of two coordinates, a single linear equation exactly gives me a line. So z equals 0 will be true on a line. And then on one side of this line, the function f of z will be 0 because its argument will be negative. And on the other side of the line, the function will be positive, and it will rise in magnitude as indicated by this color gradient, because that's the first part of the function where the function grows linearly in its argument. Yeah? So you get this. The argument itself was a linear function of the two coordinates, and then this is the output that f of z gives if f is the rectified linear unit. I also indicated w. So if z is this linear superposition of input coordinates, that is the components of the vector y, then z can be written as the scalar product of some weight vector w with y plus some bias. And so this weight vector w then also tells me what's the slope of this line where z equals 0. More precisely, w will be perpendicular to the slope. Why? Because w is equal to the gradient of z with respect to y. And you know, of course, that if I have a scalar function and I take the gradient of that scalar function, I get a vector that is perpendicular to the contour lines of this function. And setting z equals 0 is exactly one of the contour lines, so the gradient has to be perpendicular. Okay, fine. So this is one reason the structure looks like this, and so this is how training looks like at a later stage. It's already pretty good, and you can sort of see these lines, you see, here and here and here. You see these lines which are reminiscent of what you have here, because what you get in the end is a kind of superposition of many such functions, and so this is what you see here. Okay, so this is what we got. It's kind of modern art, and you can actually go to much more sophisticated examples of neural networks turning your pictures into art if you search on the web. Okay. So now once we have trained a network, we often want to understand how it operates. And this is a really complicated but also very important task. It's important for us, for example, to improve how well the network operates. We could also figure out whether maybe we have too many neurons and we can actually do with less neurons. We want to understand when it can be easily fooled by some images. Yeah, we want to understand what it is sensitive to. And in the end, maybe somehow we want to interpret what the network does. And so this is becoming more and more important, that you can interpret what your neural networks are doing. Because as we really outsource very important decisions to these neural networks, we better understand why they come to the predictions that they make. Okay. And so what I'm showing here is a very simple numerical experiment. So I trained this neural network. It was able to reproduce the smiley in the way that you've seen. But now, you know, there's a connection between the single output neuron and, in principle, all the neurons in the last hidden layer, and there were 100 of them. And now I'm doing this. I'm switching off almost all of the connections except for one. So originally, all of these last neurons of the last hidden layer would contribute to the output. Now only a single of these neurons will contribute. And the question is, what happens? And in principle, you could get a complete mess. But this is not what happens. So what I've plotted here is the images that are generated by such a modified network. There are 100 of them because I can switch on individually any one of the 100 neurons in the last hidden layer in this manner. Yeah? So there will be 100 different neural networks that I have produced by this trick. And you see that sometimes they are already pretty good. So you see, there is one neuron in the last hidden layer, let's call it neuron number 3, for example, as shown here, which when you plot this, when you plot the values of this neuron, or the values of the output neuron that is connected to it, already reproduces practically the image. Maybe not the right values, but it reproduces the most important structures. And then there are many other neurons which reproduce only part of the features you see. For example, only this circle, or only the eyes. And maybe there were also some where you only got the mouth. Yeah? So you see that one thing is clear from this picture. We probably wouldn't have needed so many neurons in the last hidden layer. Yeah? Because even if I just take, I don't know, 3 of them, then apparently they already have all the information that you would need to get a good reproduction of this image. Yeah? So probably it could also be that you could completely get rid of this last hidden layer and still get a good reproduction of this picture. And this is the meaning of this. Okay. So the last hidden layer was already pretty good. This is another numerical experiment. This is when I, again, look at the connections between the last hidden layer and the output. But now I don't only switch on one of the connections, but for example, I delete some of the weights, deleted the first 50 of these weights, deleted the last 50 weights, and so on. And you see, as expected from the pictures we just saw, I get pretty good representations. And then I can play the same game in lower layers that are closer to the input. And again, that is interesting now to compare this against what we just saw when we do things to the last hidden layer. Because, for example, here I took the weights from the second hidden layer to the last hidden layer, so one layer below, and then I start deleting, and then I already see much more, shall I say, distorted images. Yeah. So what that tells me is that in the very last hidden layer, what enters there is already pretty close to the output image, so it's very close to the final result that I want. Whereas in the lower hidden layers, the meaning of the neurons is much more abstract. And so this continues if I go further down in the layers. I get even more weird images. Okay, so this was an example of trying, our first example of trying to what happens in the neural network. Now I want to discuss a little bit the hyperparameters, because they influence what you will see in training. And the first we encountered, apart from the network structure, was this learning rate. Remember, the learning rate tells me how far do I go along the gradient of the cost function. I take the gradient with respect to the weights. I change the weights in this direction, but how far do I go in each step? So that was eta. And so this is, again, a plot of the cost function of the sort that you already saw. In the beginning, it decreases quickly, and then it levels off, but it keeps getting lower and lower, and that's good. So the network keeps getting better. Now, I increase the learning rate because I say I'm impatient. I want training to proceed faster. And sure enough, if I double the learning rate, you see, the slope in the beginning is much steeper, and I learn faster. And I go to very good approximations already much earlier. This is obviously good. And I can increase this even further. And here you see already first signs of what we will also discuss in the following. Yes, maybe sometimes the slope is even steeper, but then you also can get very large fluctuations, which may not be what you wanted. Okay. So here I plotted, so this was about the learning rate. Now here I want to make another point. Learning is a stochastic process. So in this plot I really keep exactly the same parameters. The eta is the same, the batch size is the same, it's the same network structure, the same number of neurons. The only thing I do is I run the training multiple times. And each time I initialize my weights randomly. This is also what we did all the time before. And that defines a new training run. Yeah? So the only thing that changes is the random initialization of the weights. And so what you can see here is that Well, qualitatively, of course, the behavior is the same. Eventually, you will always go down to small cost functions, so that is nice. But you see very large fluctuations. You see very large fluctuations. So for example, in the blue line, you would say, oh, already here at a very early stage of training, I got a very low cost function. But then if your colleague also runs their program, then you maybe see at the same stage still a very high cost function. Yeah? And so this you cannot avoid. So there's a stochastic component in all this neural network training. It's a very complicated nonlinear stochastic process. Okay. Then there's another point. What about the batch size? Yeah. So here I took the drastic step of going from batch size 1000 down to batch size 20. Yeah. So in a single step, I average much, much less. And so as a consequence, my estimate of the gradient is much worse. There's large stochastic fluctuations. Now this doesn't matter so much if the learning rate is nice and small. If the learning rate is small, I don't move very much in this stochastic direction. And then as I take many steps, one after the other, I effectively average over all these stochastic samples, and it becomes okay again. But if the learning rate is large, like this eta equals 1.0, that's this cyan line, then, as you see, I have very large fluctuations. Here it seems nice, then it fluctuates up in a large spike, and so on. So that's because you take very big steps in random directions, and that's not good. So how can we analyze this in a little bit more detail? What we can simply do is we can ask ourselves, okay, how does the cost function change when I do one such learning step? And so now C is the cost function. It depends on the weights, W. And here on the left-hand side, I wrote down the cost function evaluated not any longer at the old weights, but already at the new value of the weight. So that's W minus eta times the gradient. That's the single step that I took into the direction of the gradient. Now, I want to know how this changes. Well, if eta is small enough, I can do Taylor expansion. The argument is still W up to a small change. And so, and so I want to do a Taylor expansion. And so this is C of W, which is the evaluation at the initial point, minus eta times the change in the argument, which is gradient of C, times the gradient of this function itself. But the function that I'm evaluating, again, is the cost function C. Yeah? So I end up with a funny situation that I get the gradient squared. But this is, of course, exactly what I need to have, because the gradient squared is now guaranteed positive, because it's a square of a vector. And so, since the learning rate, of course, is also positive, I'm guaranteed that I take a step down in the cost function. So the new cost function is the old one minus something positive. This is, of course, the whole point of gradient descent, that if I go along the negative gradient, I'm guaranteed that my function decreases. Okay. Now, there's, of course, a catch here. There would be terms higher order in eta, and also our estimate of the gradient, remember, was a stochastic estimate. It was not the true gradient. And so we can have two problems. So the first is the step is too large, the learning rate is too large. In this case, this Taylor expansion should be carried out to higher orders, and then I don't exactly know what happens. So for example, if you think of a parabola and I take a step in the direction of the negative gradient, but I don't take a small step, but a very large step, I completely overshoot the minimum of the parabola and end up on the other side where the values already rise again. So that would be bad. So taking very large steps is not so nice. And the second thing is maybe my approximation of C, or rather the gradient of C, is bad. Because remember, we do a stochastic sampling. If I take a small batch size, then my approximate gradient fluctuates very strongly. And then this is not true any longer. So in this expansion, maybe I'm interested in how the true cost function changes. So one of the gradients is the gradient of the true cost function averaged over all training examples, the ideal cost function. But the other gradient that is entering here in my training step, that would be my stochastic estimate. That is a bad estimate of the true gradient. And it could even be that this doesn't even point correctly in the direction of the true gradient, and that would be bad. And eventually I could even have a step up in cost function. So if you look very closely, or not even that closely, here very obviously the cost function goes up and down all the time. If this were a perfect gradient descent, it should always go down. It should never ever go up again. And this is precisely this effect that I have these stochastic steps. Okay. Any questions about the gradient descent? No. Okay. But the summary of all of this is still optimistic. Namely, programming such a neural network is actually not that hard. Compared to other programs, these 30 lines of code, once you know the algorithm, that's not so much. And now you could really use this 30 lines program to do all kinds of things. Yeah? You could invent your own problems. You could, for example, go to image recognition. Yeah? You could upload a very large training database of cats and dogs, and then the output neuron would be, I don't know, it would be 1 for the cat and 0 for the dog, or you have multiple output neurons if you have multiple categories, and the input neurons would all represent the pixel values of the image. And if you just run it for long enough on this large database, you would be doing image recognition with this 30 lines of code, basically. But sooner or later, you want more flexibility and extra added features. For example, you would say, this sigmoid function or the ReLU function, maybe I can find even better nonlinear functions. Or you say, oh, this learning rate, I always have to choose it by hand. I don't like this. I know from other examples in numerics that in principle there are adaptive schemes. For example, if you solve a differential equation, you maybe don't even fix the step size yourself, but the solver can figure out the good step size for you. Maybe we can have something similar here, which would be called adaptive learning rate. Or maybe there are smarter ways of constructing my network, and we will come to them. Convolutional networks is one example. And so then you would start to expand your 30 lines of code, and they become 100 lines of code and 1,000 lines of code, and it becomes a lot of work. But maybe still 10 years ago, this would be the usual way to proceed. Luckily, nowadays, there are solutions. Yeah? And so in the last, I don't know, 5 years or so, computer scientists have come up with very nice frameworks, that is packages that contain many functions that do everything for you in terms of these basic neural network training tasks. So all of the backpropagation, the forward propagation, the adaptive learning rate, and all these more advanced functions, they will be included in these packages, and you don't have to program them yourself. And for the purposes of this lecture, of course, I don't want to jump around between different packages, but I focus on a particular one, which is called Keras. It's built on Python. Python is a very nice interpreted programming language, so this having Keras there is very convenient. You can set up and train a network in a few lines. We will have examples in a moment. And if you want to look behind the scenes, it is really based on some underlying packages that do the low-level stuff, like the actual backpropagation. And such packages carry names like Theano or TensorFlow. These packages also know how to execute code not only on your CPU, but also on graphical processing units, so it's accelerated. And all of this you don't have to care about, yeah? So this is all built in, so you can concentrate on your application, and this is very nice. Still, it was important to me to show you how backpropagation really works and how you would program it in Python, so it's not just a mystery for you. Okay, so here's how the developers themselves describe Keras as a high-level neural networks programming interface. Okay, and so let's discuss how this looks like typically. So, of course, at first you have to say things like, I want to import the functions that are available in the Keras package, and it depends a little bit on the way you installed it on your computer. I think when you did this programming session, when you did the tutorial, they showed you how to install TensorFlow, and inside the TensorFlow package, I think there is already a Keras package, so maybe this is what you were shown, right? So this may vary depending a little bit on your installation, but essentially you load into Python the routines that Keras provides. And then you want to go ahead and define a network. And so, for example, let's again take this neural network example that we just had in order to approximate the smiley with the 2 input neurons and the 1 output neuron, and the 3 hidden layers in between with these sizes. And so now, how would you write this in Keras? I mean, all these 30 lines of code that you wrote before in order to do the backpropagation, you don't need to write. This is included in the package. And so you just have to tell it, oh, I want to start a new neural network. And so this is what happens in this line. You say, I want to start a new neural network. I will call it net. And please initialize it to the default neural network type, which is sequential, which is what we've been talking about all the time, which is just one layer after the other, nothing more complicated. If you're a professional, you can also construct much more complicated arrangements of layers where maybe the neural network splits into 2 branches like a hydra, but for the moment we don't need this. Okay, fine. So you say it, let me start a neural network. And then you just use this net.add function in order to add one by one the layers of the neural network. And for each of the layers you still have to specify a little bit of information, namely in particular, of course, the number of neurons. Yeah? So this first layer, there are different versions of layers, but the simplest type of layer is called dense. Dense refers to the fact that you say, I have connections between all the neurons in the 2 adjacent layers. Everything can be connected to everything, so I get the maximum number of weights that I can choose. Later we will learn different examples, but this is the standard type of layer. Okay, fine. Then you say 150 neurons, please. It's as simple as that. And then let me just jump for a moment to the last part here. There you say, what is my nonlinear function? Each layer can have a different nonlinear function, but here I just choose the ReLU function, and it's called activation function. Activation function like in biology, so this tells me when there's a lot of input signal to the neuron, how much it gets activated. Okay. Now this is the first hidden layer that we are talking about, and because it's the first hidden layer, you have to tell it how large was the size of the input layer. For all the subsequent layers, this is no longer necessary because one layer is stacked above the other, so you always know what is the input layer. It's always the preceding layer. But for the first hidden layer, you need to specify, and this is done here, and this just means the input layer has size 2. Okay. Okay, and then you go and add more hidden layers. This is again with 150 neurons, same activation function, 100 neurons, same activation function, and then finally the output layer, which has 1 neuron and the same activation function. And that's it. Yeah? So in the same way you would prescribe arbitrarily complicated networks with different activation functions, also different structure here instead of the densely connected layers and so on. But that's it. So now in principle this sets up the structure of the neural network, but you still have to tell it a few things. Yeah? So first of all, you want to tell it, what's my cost function? we talked about the quadratic cost function, which is the standard case, but you want to tell the neural network what it should choose. You also want to tell it things like, how do I want to proceed in training? Should I do this simple stochastic gradient descent that I was talking about all the time, or something more sophisticated? And that comes all in this particular step that is called net.compile. Why is it called net.compile? Well, you see the way these modern frameworks like Theano or TensorFlow or Keras that builds on them work. The way they work is that first everything is treated completely symbolically in an abstract way. So at this point up here, you do not yet literally initialize large matrices that contain all the weights that you would need, the 100 times 150 different weights and so on. That does not yet happen. It just keeps track of a symbolic structure that lays out the structure of the neural network. And then only then when you say compile, does it take this into something that can really be executed. And it would be also at this step that it's decided whether this will then run on a CPU or on a GPU. Yeah? So here it can really optimize things for the way you will run it. Okay. So this is why it's called compile. And then you give this kind of information that I just mentioned. For example, you say, what's the cost function? Now, the cost function also goes by another name. Sometimes it's called the loss function. Anyway, cost or loss, it's the bad thing that you want to minimize. And so here the loss is the mean squared error, which is precisely what we've been talking about. So you take the deviation between the true result and the neural network result, you square it, and you average it over the training samples. And that's the mean squared error. We will get to know different cost function for different opportunities later, but this is the standard thing. And then you tell it, once you want to do the training, how the training should be done. So the training is called also optimizer, because you want to optimize the cost function. You want to make it as small as possible. And so here, out of the many different optimizers that Keras has available, I'm picking the simplest one that almost no one uses anymore. And it's just for comparison, it's the stochastic gradient descent. SGD stands for stochastic gradient descent. That's what I've been talking about. You take a small batch and you take the gradient. And then the LR parameter here, that's exactly this learning rate, which we called eta. Yeah, so the learning rate here is just, I set it to 0.1. Okay. Then there's a last step, which is called the metrics. That's a small detail. In the end, during training, the Keras routines can give you a lot of different measures as to how well the network is doing during training, and you can choose these measures here, and here it's a particular one, accuracy, and you can look this up. Okay, so this is just what I just said, just to remind you. And now, okay, now everything is set up, everything is compiled, everything has been specified. So what remains to be done is only the actual training. And so there's one thing which I will not here write down, which is this routine that I call make batch. That is something that you would provide. That is the routine that we already discussed for when we ourselves did the neural network code. Yeah? This is where you produce all the training examples. But once this is specified, and this is something I specify, it's not an official Keras framework or interface. This is simply something I specified. So now I would specify, for example, the batch size, the number of batches. I like to keep track of the cost function during the training. So I initialize a Python array with zeros that has the length 200 in this case. And now I just loop through all these 200 batches. And each time I produce for myself a pair of input and target. So the input value is, say, a randomly placed point on this two-dimensional space in the case of the image learning that we just did. And the target would be the target value that my network in the ideal case would produce if it were properly trained. Yeah? And so this make batch routine I am assuming here this make batch routine returns them. And at this point it becomes really important to keep track of the details of how the arrays are structured, yeah, because otherwise this will not work, otherwise it will just break. And so, fortunately, of course, I set up the code that we discussed before so that the structure of these arrays is exactly the same as it is now in Keras, so you don't need to learn anything new. For example, this input array would be an array of the dimensions batch size times 2. So the first index has batch size entries because there are that many training examples in a batch, in this case 20. And the second index would correspond to the 2 input neurons. So it would, the second index only takes the values 0 and 1, because in Python the index starts at 0. Okay, fine. So that's the input array. And then there's the target array. It has dimensions batch size times 1. So again, 20 in this case. And then the 1 comes from, in our particular example, the 1 output neuron. If you had 7 output neurons, there would be a 7 there. Okay. And then, once you have done this, now you can call a Keras routine for convenience, which just says train on a certain batch, and you give it the array that holds all the inputs and the array that holds all the outputs. And this will, well, train on this batch. And it will also return some numbers that tell you how well it is doing during training. And the first of these numbers I'm interested in, because of the first of these numbers is actually the cost function at this given moment during training. So the first, so the output will be an array. The first of these numbers I pick out by index 0, and then I write this current value of the cost function into my array that keeps track of the learning progress, so that I can plot it later on. Yeah. So this is all I do. Yeah. So on this slide, the only Keras-specific routine is this train on batch, which I'm calling one after the other for all my batches. Okay, and that's it. And then you get your network trained. But eventually, once the cost function is very small, you say my network is trained sufficiently, I still want to evaluate it. I want to apply it. After all, I'm not doing this for nothing. I'm training my network so that eventually I can apply it to get very quick, approximate predictions on some given data. And so that is even easier. Here you would just use the Keras routine predict on batch. The input is again such an array that specifies all the input values. Now, of course, you don't need to specify any target values because there are none. You want the network to tell you what's the correct output. And so that will be the return of this function. So y out will now hold an array of dimensions batch size times the number of output neurons. So these are the predictions of your neural network. And that's it. So you see things become very, very simple once you're using one of these frameworks. So setting up the network is simple, telling it what is the loss function, what's the optimizer, that's simple. Training it is simple, and predicting it is simple. Yeah? There are, of course, various convenience routines related to this, but this is all you need. And so when you actually now do one of these networks, when you really want to do your own project, probably the function that you will worry most about is this make batch, when you really create the training examples. Well, either you did those in a database, loading them from a database, or you really run simulations or do something more advanced. So this is the part where you will probably spend the most lines of code. Okay. Well, are there questions about the principal concept of Keras at this point? Did the installation go well last time in the tutorial? Yeah. Was it also mentioned that you can actually try out some of this stuff directly on the web in this Colab, Google Colab space? Maybe I should send around the link. So whenever you cannot do it on your own computer, then there's a website called colab.research.google.com where you have basically a Jupyter notebook online, and TensorFlow is installed and you can just try out things. So that's also easy. So in principle, on your cell phone, by opening your browser on your cell phone, if your cell phone is good enough for you, then you could start programming neural networks without installing anything using Colab. Okay, fine. Okay, and so here's just one further example that I like to show. There's an even more complicated picture, again the same kind of network, after training with lots and lots of samples, but in this case I already wanted to speed up training, and I picked one of the smarter learning schemes that we will actually learn about later with an adaptive learning rate. In this case it's called ADAM. Does anyone of you know which picture this is, except for those who have seen these slides before? You don't recognize, you still don't recognize. It's a woman and she's connected to Erlangen. How well are your neural networks trained? Yeah, what's your guess? Yes, it's Emmy Noether. Yes, thank you very much. So yeah, so a famous mathematician to originate out of Erlangen. Okay, so this training works and it's really convenient. Yeah, that was the solution. Okay, so are there any questions up to now to this part? Otherwise I will go to the next example. Okay. So you know, what we did right now, you have to realize, of course, was very simple. It's still amazing that such a generic ansatz as a neural network can learn this image, so to speak, can learn to map the input coordinates to the color values. But this is not the usual application of neural networks. So the usual application of neural networks is really, maybe you have many images and you want to recognize them. And one of the most famous early examples, already from the 90s, is this handwriting recognition. So here you see a lot of handwritten digits, and the typical application of trying to recognize them is in the postal service. Yeah? You get all these letters, you want to sort them automatically. There's this zip code, the postal code, consisting of some of handwritten digits, and you want to have them recognized by a computer. And the problem is obviously that everyone writes these digits differently. So you still have to be robust and recognize them even if they look very different. So even if I don't know, if the 4 here and the 4 up there, and they all look very different. Okay. And so one of the nice things is that computer science people and also companies that have applications like the Postal Service, they start to compile big data sets and post them on the internet. So if you think you have a very good machine learning technique invented, then you can test yourself on these large databases. And this particular one is called MNIST. And so this particular example will be very nice because we learn many different things. We learn for the first time here how to distinguish different categories of things like dog versus cat or digit number 3 against digit number 7. We will also get to know another kind of nonlinearity, which is neither the sigmoid nor the ReLU function. It's called softmax, and it's particularly well suited if you want to have a probability distribution as an output. We also will learn a new cost function, which is not the square deviation, but it's the so-called categorical cross-entropy. So it's actually related to the entropy, to the logarithm of p that you know about in physics. We will learn something about how to split all the training examples more precisely into different sets of training samples. And we will learn something about a bad problem that's called overfitting and how to solve it. Okay, so what we want to do is we want to take one of these images. In this case, they are 28 by 28 pixels. So not too large. This was one of the early training sets, so when computers were not yet so fast. So this already corresponds to 784 grayscale values, which have to be fed into the neural network. And we will take these training images, feed them into the neural network, and as output, I want to have something that tells me what digit am I looking at. Now, in principle, you could take a single neuron. You could say that the neuron should give me 0 if the input was a 0, should give me 0.1, for example, if the digit was a 1, 0.2 if the digit was a 2, for example. This would just be a choice. But that is not very robust, this way of encoding the output. And so what people like very much, if they want to distinguish between different categories of images, for example, is to have more output neurons, and each neuron is responsible for one of these categories. So in this case, since we have 10 different digits, we would have 10 output neurons. And the idea would be that if this is really recognized as an image of the digit number 6, then this neuron that is responsible for the digit number 6, that should be activated. So it should have a high value. And if it's digit number 3, then it should be a high value at digit number 3 at this particular neuron. This way of encoding things in this large string of 0, 0, 0, 0, 1, 0, 0, 0, 0, this is called one-hot-encoding. Because, so to speak, only one of the neurons is hot, it is activated, and all the others are 0. Okay, so this occurs very often. And I want to really make the distinction between what we did so far in our example and what we are doing now. Even so far, we could have taken one image, but then we would only train on this particular image to reproduce it, to turn the coordinates into the pixel value. So that was learning one particular image. Now we want to do something much more powerful. We now have an input that consists of all the pixels of a given image, so many more than just 2 coordinates. And the training set does not consist of all the pixels of one given image. The training set consists of thousands and thousands of different images. And the output should not be the color value at 1 pixel of an image, but it should be the category that tells me what this image represents. So it's very different, but of course the underlying neural network in principle is structured in the same way, except it has more input and output neurons. Okay. Now, the neural network will never be completely sure, because who knows whether this is a 6 or it maybe was another digit that was written badly. So what we typically can expect is that one of the neurons will have a high value but not perfectly 1, and the other neurons will have low values but not perfectly 0. And so the way to interpret this is to say, oh, maybe my output represents probabilities or the likelihood that this is one or the other category. So that is a useful way of thinking about this. And if, for example, the neural network would then come up with 2 of the neurons having almost equal numbers, 0.5 or so, then you could interpret that as the neural network is not quite certain, and it assigns above around the same likelihood to these 2 categories. Okay. So now, how to do this in a neural network? The problem you see is probabilities should always be normalized. If you take the sum over all probabilities, you should get 1, obviously. If each of these neurons would just be the usual usual neuron in the output layer, and we have, say, ReLU activation function or so, their values would be sort of independent, and you wouldn't be guaranteed that they sum up to 1. Yeah? So you want to enforce this. You want to invent a step from this last output layer, from the last hidden layer to the output layer. You want to invent a step that makes sure that normalization is obeyed. And this is done by the function shown here. So imagine that These are the neurons of the output layer. For each of these neurons, you would calculate the corresponding Z value. Remember, this was this linear superposition of the preceding layer neurons with all the weights and biases. But now you still have to apply a nonlinear function. And you could apply the sigmoid or so, but that only guarantees you that the values of each individual neuron are between 0 and 1. It does not guarantee you that the sum over all the output neurons is equal to 1. And so you introduce another nonlinear function, but this time it will be a nonlinear function that depends on all the values simultaneously. It has to, because it has to ensure this normalization. So the nonlinear function is given here. So imagine you have all these Z values. You take the exponential of those. So this already ensures that you automatically get something that is not negative, because the exponential of a number is always positive. I mean, the exponential of a real number is always positive, even if the number itself is negative. That's fine. That's good for a probability. But then you want to make sure that normalization is obeyed. And so what you do is simply you divide by the sum over all these exponential factors. Because if you do this, then you get something that is normalized. You can check this for yourself. If you sum this result over all j, then of course in the numerator you will have the same sum that you have in the denominator, and it cancels and it will be 1. Yeah. So this, applying this type of function to the output neurons automatically ensures that you get a valid probability distribution. And so this is, you could view as an activation function, and it's called Softmax. So it's a bit funny name. So the way to see this is basically something like this. So imagine you have these Z have very different values. Some are very negative, some are positive, and then there's one which is much, much larger than all the others. Yeah? And you want to identify which one is it that is the largest. Well, if you apply this kind of function, this largest one will automatically result in a value of almost 1, and all the others will result in a value of almost 0, simply by the way this is constructed. So you get a 1 at the spot where you have the maximum value. And it's called softmax because, well, it's not precisely 1, and if 2 of them are sort of equal, you get 0.5, 0.5. So it's a smooth way of doing this. By the way, if you look at it very carefully, you can also recognize that this is structurally very similar to the sigmoid function. You can view this as a multivariable generalization of the sigmoid function. Okay. Now the beauty of Keras is that it's super easy to implement this. You don't have to program this yourself. You just say that your activation is no longer the ReLU, but the softmax, and that's it. Yeah? So as soon as you know what you want, you get this by one line. Okay, so that was the how to generate a nice output that can be interpreted as a probability. Now I want to discuss how we construct the cost function. In principle, you could take a quadratic cost function. You take the real one-hot-encoded output, 0, 0, 0, 1, 0, 0, and the output produced by the network, which is not so completely nice. You take the differences and squares and add them. That would be okay. But there's something that is much more suited to this case where you have probabilities. And it's actually based on the entropy. And so you have learned statistical physics, presumably. So you know how to calculate the entropy. So for any probability distribution, I can calculate an entropy. And the entropy is a rough measure of how spread out the probability distribution is. If it's very spread out over the various possibilities, then the entropy is large. If it's concentrated tightly in one of the possibilities, then the entropy is small or even 0. Yeah? And so for any probability distribution given by probabilities pj, I'm here talking about a discrete one, you just sum pj times log pj, and you put a minus sign. So the minus sign is there to make the entropy positive. Yeah. Okay. So there are several nice features of the entropy. It's non-negative, and also, and that's very nice in physics and otherwise, it's additive if the probability distributions factorize. So if you have multiple variables, multiple random variables, then you would probably not write pj, but you would write something like p of I, comma j. That's the probability to get this combination of value I and value j, okay? And you would be able to write this, to factorize this as a product of two independent probabilities, one to get the I and the other to get the j. And then it turns out if you insert into this formula for the entropy such a factorized probability distribution of independent random variables, then the end result is just the sum of the individual entropies of the individual random variables. So that's very nice. In physics, this just means if I have two boxes filled with gas, the overall entropy calculated according to this formula happens to be the sum of the entropies of the individual gas containers, and this is as it should be. Okay, so that's the entropy. And now we define a cost function that looks like the entropy. Yeah? So if your output of the neural network, here again called y, is representing a probability distribution, and I want to compare it against a desired target probability distribution, then I can set up a cost function of this sort. So it looks like the probability, like the entropy. Remember p log p. And here, it's however not in this so-called cross-entropy. You want to compare two probability distributions. So instead of having p log p, where it's the same probability p that enters twice, here you have two different values of the probability entering. This is the target distribution. This is the output of your neural network. Yeah? And so there's a little mathematical exercise that you should do as your homework to check that this becomes 0 exactly for the correct output. Does it? Yeah, in our case, in our case it becomes 0 exactly for the correct output, because the correct output is this one-hot encoded probability distribution, which is 0 everywhere and 1 at one spot. And for such a probability distribution, the entropy is 0. You can check this here. So when p is 0, you get 0 times log 0. So that needs a little bit of interpretation. The log of 0 in principle is minus infinity, yeah? But the log goes to minus infinity so slowly that it's completely overwhelmed if you multiply it with a 0. You could also take the limit. So x log x, limit x going to 0, that will tend to 0. And then, on the other hand, at the one spot where this probability is 1, you have 1 log 1, and the log of 1 is simply 0. Yeah. So it gives you 0. And so here also, if y target is equal to this one-hot encoding, you get 0. And again, the nice thing is you don't need to program any of this. Yeah? So Keras provides for you this cost function. So instead of saying that the loss should be the mean squared error, you say it's a categorical cross-entropy. It's called cross-entropy because, well, it's an entropy that compares two different probability distributions. It's categorical in the sense you're using it here because you take categories of different labels as outputs. Fine. And so why do I bring this up? So first of all, people like to use it a lot. There's still one question here. Why I take the log of y out and not the log of y target. We will see in a... So in principle, all of what I said here would still hold if you do it the other way around. We will see in a moment why this is advantageous, actually. Yeah? Okay, but good question. Okay. So why do people like it? Why do people like to combine these probability distributions, that includes the Softmax construction and so on, with this categorical cross-entropy? And it has to do with how the derivatives look like and therefore how the training progresses. Remember that when we want to train, we take the derivatives to calculate the update in the stochastic gradient descent. And so we need the derivatives of the output neurons with respect to the arguments that I put into these output neurons. Yeah. And one of the problems that the sigmoid has, and the softmax is similar, is that it obviously has these long flat parts where it has saturated. So if you put into a sigmoid function an argument z that is much larger than 1, say, it always will stay 1. Yeah, it doesn't really change. The value doesn't really change. As a consequence, the derivative is 0. Now, why is that a bad thing? Or it actually becomes 0 exponentially fast, yeah, as you go to larger arguments. Why is that such a bad thing? Well, if the derivatives really are 0 or very, very small, then there's no training going on, yeah, because training happens by going along the derivative with respect to the weights. So when the derivatives become too small too quickly, that's bad. And so this is a catch that would also be there for the softmax function, but it's a catch that is cured by using this categorical cross-entropy function. And so I don't know whether we want to go through the details of this. So basically this is a little homework exercise that you can do for yourself. This is the softmax function. I calculate the logarithm. You see the nice feature that this logarithm takes the logarithm of this exponential, which again reproduces the argument, obviously. Yeah? So now if I take the derivative, well, there's these more complicated terms for sure, but there's also simply the derivative of the argument. That's very nice, actually. Now let us compare this to the situation where we apply the quadratic cost function. So again, the same nonlinearity, that's the softmax. But now I have this quadratic deviation, so I take the derivative. You know how to take the derivative of the square, that's not a problem. That would be the deviation between the target value and the output value, so that's okay. But then you have this derivative of the output value standing here. And that's really a problem, as I just said. There is the slope of the sigmoid, or the softmax in the same manner, that becomes exponentially small as you go out to larger values. And so that would make training really, really slow. So that's what we don't like. And so here you see immediately it was important to apply the logarithm to the output of the neural network. Okay. So now let's see what happens. Just let me mention this as one example. Again, you can find the code on the website together with the training images. Now we want to train on this postal code digit recognition example. The training inputs, well, you can store them in an array. The size is the number of samples times the number of pixels inside each image, which was on the order of 700 or 800. Yeah? The training results, again, that's the number of samples times the second index is the number of input neurons, number of output neurons, that should be. And those are 10. This is this one-hot encoding where we have 10 digit, and for if we have a particular training image, we should get a 1 at exactly one spot. Okay. And so now I want to introduce you to another Keras function. If I already have this large set of all potential training inputs loaded from a database, for example, then I don't even need to loop myself through various batches. Keras can do this for me. It's called the fit function. You give it the training inputs, this whole array, which may be really large. You give it the training results. You say what should be the typical batch size, 100, let's say. And you tell it how many times should it go through the full set of training examples. Always splitting it up in all these small batches, yeah, but how many times should it go through all of these, in this case, 50,000 training images. And then it does it for you and keeps track of how well it is doing and so on and so on. So you don't even need to loop through anything here on your own. So probably the most difficult part of writing this program will be the part where you actually load the images into the memory. And so here's the accuracy during training. So this accuracy is defined not as the cost function, but really how much you recognize in the right manner. So for each result, you would say, oh, the network thinks this is digit number 3. Let me look it up. Is it really digit number 3? And then you check whether that's true, and then you say, oh, it's true in 97% of the cases. Okay. And so this looked good. So it seemed like in 97% of the cases, here at the end of training, you were getting the right results. But now you take a bunch of test samples that the network has never seen before, and you test whether this is really true. And you see, wait, there's 7% of the test samples that it recognizes incorrectly. Here I show some of them. You have to admit that some of them are a little bit difficult. Yeah? So I think in quotation marks I put the result that the network predicts, and then in brackets I put the result that is really true. And so for example, here it thinks this is an 8 because it doesn't quite see that this is split open. Here it thinks it's a 7. Well, maybe that's not so great. Well, here it thinks it's a 5. Well, it was obviously not a 5, but you also have to admit that this 3 was quite tilted. So you can sort of see why it has problems. But why does it get things wrong in so many of the test samples, in 7%, even though we thought we were up to an accuracy of 3% error? Okay. And there's one thing that is very important to realize here. So if you assess the accuracy by always comparing against the training examples that you're already training on, you may get results that are too optimistic. Yeah? You may be too optimistic. And what one really needs to not be too optimistic, and I tell you why this is too optimistic, is you need to compare against samples that the network never sees during training. Because what you really are interested in is not whether the network can kind of memorize all these training examples, which it will do if you teach it many, 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 many times, but you're really interested in whether it can properly generalize to other examples that it has never seen before. And so that's the challenge. And so this is how people honestly deal with this problem. So you have a large training set used for training, let's say 45,000 images. But then you keep out of the training a so-called validation set of 5,000 images, for example. I'm just putting numbers there. And then during training, as training progresses, you always test the accuracy on this validation set. And then you can see how the accuracy is going up in time. And that's a honest assessment, because the network has never been trained on these particular ones. So it cannot somehow memorize them. They are independent. And then finally, of course, you have your real application or your test set. These are extra images that have never been even used during training. Maybe you didn't even know them. Maybe they were not even generated when you try to train, and you want to apply the system, the neural network, on these images later. And so this is what we will discuss next time. I will leave you with this little riddle here. So here you see I already mentioned it in words. This is the accuracy on the training data. So when you not only train on these images, but also assess the accuracy with respect to those same images. And the green curve is the accuracy on the validation data that you're keeping separate, that you're never training on. And as you can clearly see, in the beginning they are sort of similar, but then after some time they are different. The accuracy on the validation data is worse, and it even decreases slowly over time. So things get worse even though you're training. And that is something that we want to discuss next time. Okay, so are there more questions here? Well, if not, then that's it for today. Thank you very much. See you on Wednesday, actually.